In this video, we're going to explore the dot product again, but we're looking at an alternative definition for it. We're calling that the first version of our dot product said that if we have two vectors, v and w, we can compute that dot product, the value of that dot product, by taking the length of each vector separately and multiplying those, and then multiplying by the cosine of the angle between them. That form is helpful when we want to be thinking about angles between vectors, but a lot of times we have components for our vectors, and there it's not as obvious of how we would get the angle between them. Fortunately, it turns out that this definition of the dot product is not the only one that works. We can also take the dot product of two vectors by literally taking the components. Here we're taking a three-dimensional vector and thinking of it as lambda1, lambda2, lambda3 as the x, y, and z components. And for the other vector, calling them here mu1, mu2, mu3, we take the x components and multiply those. Then we take the y components and we multiply those down to here. And last but not least, we take the z components and we multiply them. And once we found those products, we simply take the sum of those three products. Notice that this again gives us a scalar value in the end, which is what we expected from our earlier definition as well. Here we had a scalar times a scalar times a scalar, and we end up with a scalar here as well. It's important to note that it is not obvious that this way to compute a product is even close to the version that has the angle involved. We don't see the angles here, but somehow miraculously these do actually become the same value. And we're going to demonstrate that next. Ideally, we would prove this. You can see a proof in your textbook or any other textbook in first year calculus. However, we're going to do it more through a demonstration just to reinforce that it would work in practice with a relatively simple example. So imagine we have the vector 1, 1, and 0, 3. Let's call that our vector v and that our vector w. If we do the component dot product, that is certainly the simplest case here because we have the vectors and components. V dotted with w is 1, 1 dotted with 0, 3. And to do that product, we take the x component and x component, so 1 times 0, and then we add the y component times the y component, 1 times 3. So we end up with 0 plus 3, or 3. Fair enough. What about the angle notation, or the angle version? Well, if you look at the angle formula, we're going to need to draw those two vectors. And again, notating where we are, here's x, here's y. The 1, 1 vector is up at a 45-degree angle. And the 0, 3 vector is all vertical. So it would be up here like so, 0, 3. And we can tell from the diagram then that the angle between them is going to be 45 degrees or pi over 4 radians. If that's the case, then we can take the dot product again, but now using the angle version, angle and length formula. And if we do that correctly, the length of v is the length of a 1 by 1 sided triangle, the hypotenuse of that. So that will be the square root of 1 squared plus 1 squared. The length of w is simply 3. We don't have any component in x, so it's easier to calculate. And the cos of pi over 4, not pi over 2, my apologies. The cos of pi over 4 is one of those classic triangle ones. It's 1 over root 2. Well, that's handy because we then see root 2 times 1 over root 2, we get exactly the same value. So both definitions give the same value. Again, this isn't a proof that this always works. It's an illustration with a single example, but you can go back to the textbooks again and see how this is proved in the general case so that we can rely on this dot product with components always giving us the same value as the angular definition. We will use both the component and the angle ideas to look at this problem here. We're asked to find a vector u, which has two components a, b, so the components are there already, magnitude or length 1, and which is perpendicular to, so that involves our angle definition, to the vector 3i plus 7j, or in component notation, simply the 3, 7 vector. Okay, well, the nice thing about this angle information is that we know that 3, 7 dotted with AB must equal 0. We know that through the cos of the angle having to equal 0 if the vectors are perpendicular. And I'll use this perpendicular symbol here occasionally as a shortcut. So that's using the angle definition. Well, we can also then tie in the component definition and compute the same dot product explicitly as 3a plus 7b equals 0. Now we note that there is one possible solution already. If we have a equals 0 and b equals 0, this would satisfy the equation. However, is there a problem with that, a shortcoming? There absolutely is. We wanted to get a vector of length 1. And that is not going to be a length 1 vector, it's going to be a length 0 vector, if that's what we picked as our solution. So that's off the table. All right, well, if that's off the table, then the other thing we can do is look for positive solutions to this and see what we get. Well, what we can do initially is note that 3a would equal negative 7b's, or that a would equal negative 7b over 3. Well, that's one piece of information that helps show the relationship between the two components, the x and y components in our vector that we're looking for. We can also bring in the magnitude or the length of the vector as well. So if we need length 1, that means that a squared plus b squared, all square rooted, has to equal 1 as well. There's several ways to work with these two equations. It's entirely up to you how you do it. I would be tempted simply to sub in this a value here and start solving. So if we sub in the a value into our equation here, we would have negative 7b over 3 all squared plus b squared equals 1. And we can actually square everything here, and that'll just get rid of the annoying square root sign. And then we can expand these terms inside as well. So we'll have 49 over 9 b squared plus b squared equals 1. Then we can start factoring things, which we'll do on the next page. We have b squared, and we had 49 over 9, and we had 1b squared equals 1. Putting these on a common denominator, we would end up with 9 over 9 here, and 49 together give us 58 over 9 equals 1 times b squared. So b squared is going to equal 9 over 58. And so b would equal plus or minus 9 over 58, all square rooted. All right, if we take the positive root of that, the positive square root of 9 over 58, then the a value that matches that is going to be, going back a page, the a value, once we have b, is negative 7/3 of that, negative 7/3 of our square root of 9 over 58. Does that make any sense? Well, let's draw a quick picture. If we draw the vector 3, 7, so 3 and 7, more up than right, that is our vector here. We have found the vector u, which is a, negative 7/3 times square root of 9 over 58, or comma the b value, which we are taking the positive root to start, 9 over 58, like so. And there's an interesting thing we can do here, which is invert the scalar multiplication. Both of these have a common factor of the square root of 9 over 58. That lets us pull out that one expression from both the components. And what that lets us do is see this vector a little more easily. In fact, what I'm also going to do is pull out a 1/3, or maybe a better way to think of it is multiply this vector by 3 and then put a 1/3 out front to cancel it. So we have 1/3 square root of 9 over 58. And then I take into account that I divided by 3 by multiplying by 3 here. And lo and behold, this is a direction, or it captures the direction of the vector. All the rest of the information here was put in place to make sure that the magnitude of the vector was 1. But from here I can tell that we're going left, mostly left, and up, like so. But all the calculations would guarantee that it's length 1, and so what we would see is a perpendicular vector being constructed here, which matches our design goal. So again, what we've done is use the idea of perpendicularity to give us information about the dot product between these two vectors. And then we use the component nature of the dot product to be able to solve for the vector we were looking for and get a non-obvious answer to this particular problem. It's worth noting that there are other answers to this. In particular, we skipped over the b value that was negative the square root of all that. And we can see just from a simple diagram again, that if we have the vector 3, 7, we found the vector u that was going this way. But of course, there's a perfectly valid opposite direction version, and all that is the same vector, but with the b value flipped. So we could have also found the direction u in the opposite direction, which would have been, we can actually predict that now. Let's call that u2. It would have been 1/3 square root of 9 over 58 times, going back a page, here we had negative x and positive y. What if we had positive x and negative y? That would capture that b value there, and that would be a perfectly good alternative perpendicular vector to the vector 3, 7 with unit length.